Hello and welcome to this video. In this video, we will study the algorithm of depth first search and see the implementation. Also, we will look at properties of search algorithms. Excuse me, there is something bad in throat. So, we will see the comparison of search algorithms. So, without further ado, let's get started. So suppose we have the same graph which we had for breadth first search, we have the same thing. Now the reached queue which we had for breadth first search has been replaced by a stack. And so let's see how it works out for depth first search. So first we visit 0. Then we look at the children, we see 2 and 3 are children, we put them in the stack. Okay. So I have put like 3 2, it could be 2 3 also. That depends how adjacency lists and other things are programmed. So the essence is that the children are put on the stack. Then you visit the first child and put that in visited table, and you look at the children of this new node, which is 1 and 4, and 3 is also there before 2 and 1 and 4. So we put the new children in the reached stack, and then we go on popping the stack and visiting those and keep putting the children in the reached stack. So that is how depth first search works. Now depth first search can have two implementation, one with the stack, with the reached stack, or the second implementation could be recursive, because recursive implementation and stack implementations go hand in hand. Either you can have a stack or you can recurse it. So essentially this is the same. So before we look at the implementation, let's go through the properties of search algorithms. So in general, algorithms have two properties: time complexity and space complexity. But in case of searches, there are two more properties. One is called completeness and another is called cost optimality. So let's see what these properties mean. So time complexity means that how much time does an algorithm take? Okay. And space complexity, as you know, how much memory does the algorithm consume? But completeness is a new property. It says that is the algorithm guaranteed to find a solution when there is one and to correctly report failure when there is not? And cost optimality says that does it find a solution with the lowest path cost of all solutions? Now BFS is complete if B is finite, B is the branching factor, and the state space either has a solution or is finite and cost optimal if action costs are all identical. So for undirected graphs where the action costs are all identical, BFS is complete. Even for directed graph, BFS is complete, but for weighted graphs, when the weights would be different, most probably and weights would be different, BFS will not remain cost optimal. Now B is called the branching factor or number of successors of a node that needs to be considered. So these four are the properties of a search algorithm. Note that depth first search is neither complete nor cost optimal. So for small graphs, breadth first search is recommended, but for larger graphs, BFS is simply becomes impossible because of very high memory consumption. So with this in mind, let's go and look at the implementation. So like BFS, we have defined a graph. These things remain same. We have create node function, we have create graph, join the edges, print the graph, and DFS. That is the core of the header file. As always, I have split the entire program into three parts: the header file, the driver program, and the core algorithm. So driver remains the same. We create a node of 4 nodes. Let's start with 4. We have 0 to 1, 0 to 2, 1 to 2, and 2 to 3. So we print the DFS by invoking the DFS function. And now we look at the DFS. So first we look at join. So you can create unidirectional or bidirectional. It varies. It does not really matter. I have created unidirectional joins. Create graph is similar to my previous video. So if you have not watched previous video, I will recommend that you go and watch the previous video on BFS implementation, and you will see that these functions are covered there. So create graph is covered here, create node is here, and join we have already covered. Print we iterate using the same mechanisms of adjacency list. Print means you just print the adjacency list, that's it. Now the DFS is very simple as the algorithm I have suggested. So we first get the graph and the vertex as the argument. So we pull out the adjacency list from the adjacency list linked list, and we point the temporary to the first node of adjacency list, and we mark this one and print it. Now we iterate over the adjacency list of that particular node, and if the connected vertex is temp vertex, then we mark the visited to be 0, and we iterate over the DFS, and then we move on to next node of adjacency list. So it's not big, it's just 1, 2, 3, 4 lines of code. So it's very simple. If you understand the picture I have presented, it's very simple to understand. In case of stack, you will push it over stack over here, and otherwise it is a recursive solution. So let's see this into execution. Let me zoom this and let me call GCC, and then we run this ./a.out. So DFS from 0 is 0, 2, 3, 1. Okay, now let's see if we can go from node 1. From 1 we cannot go because there is no path from 2 to 0. So what we can do is we can create bidirectional nodes, and then we should be able to cover from 1 to 2, and then from 2 to 0 we can go. Okay, so we compile this, and before that I have to make this 2, and then we compile this, and then we do this. So yes, from 2 also you can go 2, 3, 1 and 0. So 0 will come at the end. You can try to increase number of nodes. So let's add a node 4. Print, not print, join graph. We can join 4th node from, let's say, 2nd node. Okay. Oh. And then we compile this again, and then we run this. So yeah, 4 also we can visit. So we can change this main program to iterate over several things. So this is the crux of the entire logic, the DFS. Okay, and you might want to try a graphical presentation of how this works. You can trace down the function call, keep it small, and trace down the function calls, how it works. It might be easier for you if you debug through this while loop and see how it goes through the adjacency list of the graph. So with this we come to the end of this video. One thing you would note that I have not covered the time complexity and space complexity of BFS and DFS. That we will do after the next video, because in next video I will present the shortest path algorithm of Edgar-Dijkstra, otherwise also known as uniform cost search. So once we have covered the Dijkstra algorithm or uniform cost search, we will compare the values of time complexity and space complexity as well. So I hope you have found this video useful and informative. If so, please like, share and comment as much as you want. And if you are new to the channel, please make sure that you subscribe the video so that you can watch the videos, you can get notified and all when a new video comes. So thanks a lot for watching. Happy programming.